Hello friends, in this video I am going to teach how to use PEMAG for design of a transformer and an inductor. So in the screen you can see the transformer geometry with primary and secondary and also core. So the creating this geometry inside a Maxwell, uh, it's not that straightforward and it consumes a lot of time. You can see here the creating a round corners like this will take a lot of time. So here PMAG can be a great help. PMAG is a software also designed by ANSYS. Uh, where we can where it's very easy to create transformer and do the basic analysis. And further, the design made in the PMAG we can export to the ANSYS Maxwell, which will look like this. So I will show you how to make a similar type of design. Let's just start with it. So when you open the PMAG for the first time, it will show this window. So we'll just start with the design. We'll create a new file. And the first process is to bring a core into the design. So on the left hand side, you can see there are different type of scores, different by default libraries are available, like E-type, EI type, UU type. Then there are different core geometries available from different manufacturers like Magnetics, FCOS, MetGlass. So as you have seen, my geometry includes two U cores. So I'll just start with a two U cores, and I'll just open my core data sheet. So this is my core data sheet, which the geometry is this is the code for the geometry U463928. So I think uh, this core might work for me. Let's just cross verify the dimensions. Uh, we can see here. So D1 is 46, which you can see 46. Then D2 is 16. Here it is 16. Then D3 25.5, 25.5. So all the parameters are matching. So I will use this code. The To bring this core into our design, you have to just drag it into this black window. Now you can see uh, core came to our design window, and here we can edit the dimensions also. If your core is custom made or the core dimensions are the whatever the libraries are available. Uh, which are not your core doesn't match dimension doesn't match to those library. Here you can edit your core dimensions. So as my core is available, so I am going to just start with it, and I will take a double 2D model. So if your your geometry involves certain symmetry, you can go with this axial symmetry. But for now, I'll just go ahead with a double 2D. And now here the AL value is 5600. I'll just see what is the AL value of my core. 5630. So I'll just copy this. Okay. Then next part is to create a bobbin. So let's just start with it. Bobbin, here I will use a default UU bobbin. Again, the same thing, you have to drag bobbin into the black window, and then you can edit the shape of the bobbin. So the bobbin should be, I want to create a bobbin around a left limb. Uh, Around this left limb, I want to create a bobbin. Uh, so the dimension of left limb we saw, the this width was around 15. Uh, if you go to core dimensions, we can see, let's calculate the limb width. So it will be, I have to subtract D2 from D1, 46 minus D2 is 16, and if I do divide by, and these are the width of two limb, so width of one limb is around 15. So I have to keep a D3, you can see in the picture, the D3 I have to keep 15. Then I want a bobbin thickness of 2 mm, so that we can control using a D2, all various parameters, D2, D4, D5. So around a limb, how much thickness I want, that I can control using a D2. So D2 I will keep 19, as 2 mm from the both side I want, from left side of the left limb and right side of the left limb. So I'm keeping 2 mm each. So 15 plus 4 is around 19. I'm keeping. Then D1 I can keep. Let's see how much. Uh, what is the value of D1 will be required. Uh, so D1 will be, let's say D1, I want a bobbin to fill entire core. So in what we can do is I'll add this 16 uh, to, I'll add 2 into 16, that is the window width. I want to cover a entire window width by bobbin, plus I have to add a core cross section width, so which is around 15. So it gives me around 47. So I'll just put 47, D1 47. Then D4, my D5 will be the total height of the core, which is 51. And I want a thickness, a bobbin thickness of 4 mm, sorry, 2 mm each, from the 2 mm on the bottom and 2 mm on the top. So here I will keep D4 as a 47. 51 minus 4, which is 47. So just put, we'll press apply, and tada, our bobbin is created. So the next part is to create a winding. So we'll go to the winding tab, and then we'll use this default winding setup. I'll just bring this into our window, and we can start editing. So I'm going to create a transformer with a, let's say 10 turns in each primary and secondary. And you know the transformer has a 4 terminals. So I have to give here 4 terminals. If you are creating an inductor, you will just go ahead with a, you can go ahead with the 2 pins. And I will create a 3 layers. I'll show why 3 layers. So these are my 3 layers. One I will define as a primary, second I will define as a secondary, and in between I will keep a insulation layer. Let's say you are working with a high voltage design, then you might, and there is a significant potential difference between primary and secondary winding, then you need to create a insulator, you need to keep an insulator in between primary and secondary. That's why in a deep winding setup, what I have done, I have created a 3 layers. Also, based on how you are winding, winding your, how your winding is placed around the core, either you will select concentric or a top down. Top down will, I'll first show what is a concentric. Uh, so now by default, this 3 will be considered as an insulator. So first we have to convert these two into winding, and we'll keep this as an insulator, middle one as an insulator. So let's just convert it. You can convert it using this clockwise monofilar option. So it will create a one winding. And similarly for this third one, we'll keep that. Let's say if you're winding in a such way that the primary and secondary turns are based on how you are wounding it. Either you can select clockwise or counterclockwise. Or in my design, both are in a clockwise, so I'm keeping it as like this. Then the next part is to give the number of turns to this. So if you just right click on that, this properties tab will open. I'll put 10 turns in primary and 10 turns in secondary. So yeah, but still now the winding is not visible as we have not given a material of wire, or we have not defined what the material we are using and what type of a wire we are using, like either round wire we can use, square we can use. So that we have to go in this wire and insulator tab. Uh, Here you can see different types of wires we can use, either foil, Litz wire, planar, round, square, twisted. As of now, I'll go with a round wire, and you have to drag this round wire. Uh, you have to drag this round wire to your winding. Now you can see the winding. Your turns are visible, but now we'll edit the how much diameter we want. In my design, I need a 4 diameter. Insulation thickness is around 0.2 mm, and turn spacing as of now I'm keeping 0. So other parameters like resistivity, thermal parameter, this resistivity by default is they have taken for the copper, and I'm not right now interested in a thermal simulation, so I'm keeping this parameter as it is. But if you want to do thermal simulation and you want to do some thermal analysis, you can change the thermal parameters accordingly. Now these two windings are connect. We have created these two layers, but now you can see that this layer, two layers are almost touching the bobbin, but I want these two are in the center of the geometry. That you can do in the core. Here you can go to the core. Oh, sorry. Uh, that we have to do in our winding setup. So in winding setup, you can see from how much margin we want to keep from the top. Uh, Now let's do some basic calculation, how much will be required. So the total height of the available winding, we know it is a 47, as 51 is the winding height, sorry, window height, minus the, if we subtract the bobbin thickness of 4 mm, we'll get 47. This is the 47 is the available winding, available window height. So from that, I will subtract 4, 4 which is the diameter of each turn into the number of turns. So which is the height of the winding. So the remaining space, this is around 7 mm. So from top and bottom, we can create, we can keep 3.5, 3.5 mm. So we'll go to default winding setup again, and from margin of 3.5 mm, I'll keep. Now you can see the winding is now exactly in the middle of our window. If you, so now we have kept the margin from top and bottom. Now we can, now the next part is we have to connect this terminal with the winding. So that you can go to the connection tab, add. Here you can see add connection, and then uh, you have to start connecting it. I will connect 1 with 1, 2 with 2. Now you can see it has given a color to the winding. So yellow color represent A winding, which is my primary winding, and now I will do same with the secondary winding. Now our secondary winding is also connected to its terminal. It has given red color to it. Now if you see, still our design status here, you can see what is remaining in the design and what needs to be done. So core material is not defined, and also insulator material is not defined. So we will go to the insulator. We have not assigned any material to it. For now, I'll just give the default insulator, and now I will change its property. So I'll name it as a Nomex, and I will put 1 mm thickness is sufficient for me, and I have the Nomex, uh, some data of Nomex available with me. You can see on the right side. I'll just keep PEMAG window on the right side. So here you can see I have this Nomex datasheet. Let's just fill some of the details. I want a relative permittivity. Let's look at relative permittivity. It will be there in the electrical properties. The dielectric constant. It is 3.4. Conductivity 0.157, and thermal emissivity data is not available as of now. I'll just keep. Anyway, I'm not interested in thermal simulation right now. I'm just keeping this some random value, and resistivity is around 2 into 10 to power 6. So 2 into e power. But this resistivity is in ohm centimeter, and here the dimensions are ohm per meter. So I'll keep 2 into 10 to power 18 ohm meter. Now core material we have to define. So on the left panel itself, core materials are there. This is I'm designing. My core is a ferrite and material is N86. So I'll just for now choose one ferrite material. Default ferrite material. I'll put it. I'll drag it, and once that is done, we can set some of the parameters. So initial permeability value, I have this ferrite N87 material datasheet, where you can see N87, the initial permeability for the material is 2200. I'll keep that. And the resistivity is around 10 ohm per meter. So I'll keep that value, 10 ohm per meter. And the thermal conductivity, let's see that values are available. I'll just search here. No, thermal conductivity data is not available. I'll just leave this parameter as it is, because anyway I'm not performing a thermal simulation. If you are working in the if you want to do thermal simulation, then you have to set this parameter properly. But as of now, I'm not interested in doing that. So now we can see all the properties are clearly defined. Before that, let's just increase the height of this, and we'll keep height equal to 10 mm. Oh, sorry, 40 mm, because our 4 turns and 10 turns. Oh, sorry, each turn has a 4 mm diameter, and total are 10 turns. So height will need around 40 mm. So now you can see our PEMAG model is created. So further we can go ahead with the analysis of that, or we can just export this data to the Maxwell. I'll show how to do that. So now we have created our transformer model in a PMAG. Next, we can do certain analysis on this model using in a PMAG, but that I will cover in future videos. Now I will show you how to export this model to the Maxwell. There we can further do certain analysis. Uh, we can see its flux density, we can calculate the core losses, we can give certain voltage current excitation to that. That we will do in the Maxwell. But as of now, I will just show you how to export it, how to do the further analysis in Maxwell. That topic also I might cover in a future video. So to export, go to this option FEA eddy current. Before that, we have to save our design. Let's just save it. Now, uh, okay, sorry. We'll first save it. PMAG, I name PMAG TF, save. And this window will open. If you want to do some 2D simulations, you can select 2D. And if you want to do 3D, you have to select this 3D tab. I will show you how to do with 3D. And if you select this apply symmetry, then it will, I'll just open my ANSYS Maxwell window. So here you can see the geometry is created using a half symmetry. My entire transformer, uh, it has cut it down into two halves, and now as there is a clear symmetry here, I can just simulate for one half, and I can just use a symmetry multiplication of two. I will multiply the any entire result with two to get my desired result. So we can use that symmetry feature to speed up our simulation. If you want to do full simulation, you can do that as well. But for now, uh, I'll keep this box as enabled as I want symmetries. Then either you can select what kind of test you perform, what kind of test you want to perform on a transformer. Either you can select open circuit or a short circuit. For now, I'll just go ahead with the open circuit, and I'll just select either you can solve this eddy current simulation uh, and get a data, or for you can just create a model, and then based on whatever your requirement, you can either do eddy current or a transient simulation or a static simulation. So I'm just selecting the eddy open the eddy current project option. So it will start creating uh, the eddy current. It will start creating the model for the eddy current project. Now you can see it has started building the model in Maxwell environment. So the model creation process is completed now. And you can see it has created an entire transformer model automatically. We can see our primary, secondary winding here and the core. Also on the left hand side, you can see it has created a eddy current, entire eddy current model. Uh, and I'll just show you how the excitations are looking. I'll just rotate it a bit. Now you can see here it has given a current excitation. Current is going inside from this side, and it is coming out from other side. You can see that, and it has defined as current as I peak and value of I peak as a 1 ampere. That is for a primary winding. For a secondary winding, you can see it has given a current as I peak 2, and value of I peak 2, I'm guessing, will be 0. Yeah, you can see here I peak 2 is 0 because we are performing a open circuit analysis. So you can just and setup is defined here. So you can select the your required frequency, uh, and you can start the simulation. For now, I'll just skip the uh, simulation and analysis part. I will cover it in the future videos. That's it for today, guys. I hope you like the video. To learn more about ANSYS, you can follow my channel. I have made videos on some of the super helpful features of ANSYS, like Maxwell scripting. In this video, you can see the how I have leveraged this Maxwell scripting to create a model. Also, in this particular video, I have used some of the AI tools like ChatGPT along with the Maxwell scripting to automate the voltage excitation, or you can use the similar what I have done to do some other tasks. So this will definitely help you in process of automating your model creation, and it will help to speed up your design and make you more productive. As Professor and economist Richard Bardwin rightly said, it's not AI that will take your job, but someone who knows how to use AI might take. So do consider watching it. Thank you guys. See you soon in the next video.